smartly how to use energy to reduce peak loads. Another software you might know about is genetic algorithms, which is natural selection or breeding in a computer in order to find optimal solutions. And I think these are also going to be very important in smart grids. So you may already know about biomimicry. Next, please. But in this case, at the level of a city, mimicking nature comes at the level of the ecosystem. So imagine if this, next please, performed like this. Biomimicry in this case says, what would the native ecosystem be in a particular place, and how would it be performing in terms of what's called ecosystem services? And that's the level at which we mimic nature. Next. It's learning literally from the locals. Next, please. So this is, I don't know if any of you have seen this, this is Manhattan Project. It's where they looked at the island of Manhattan and said, what did it look like in 1609? More importantly to me, it's how did it function? What were the ecosystem services? The amount of carbon that was sequestered, the amount of cooling that was performed, the amount of biodiversity that was maintained, the amount of soil that was built, the amount of rainwater that was stored and then slowly released. Now the function on the island on the right, I would argue is a high-performing system. And the function on the left has got a lot to learn from the function on the right. And that's what biomimicry at the level of a city does. Next, please. So the first step, when we go in, I work for a company called Biomimicry Guild, and we are consulting biologists at the design table, and in this case at the architect's table. The first thing we do is we go into an area and we recognize that there's a unique ecological story of each area. Even if right now it is, in the case of Langfang, an already established city, this is an ecological land type. And if we were not there, there would be a particular native ecosystem on that place. And that's what we try to learn. What would be there if we weren't there, and how would it be operating? Next, please. Every place has its unique ecological dynamics. Next, please. And so what we try to do is learn from the genius of that place, meaning the ecological story, and also how the organisms are meeting their needs in that place. We try to learn from that. Next, please. So for instance, in Lavasa, India, which is a project, a 10,000-acre development near Pune, India, that we're working on with HOK, one of the first things we saw in that area, that hill town area, you can see those waterfalls in the background there, very fragile soils. It's an area that gets 9 meters of rain in 2 months. And for much of the rest of the year, it's essentially a drought. It's very, very dry. So the soils are extremely fragile. That was one of the ecosystem dynamics that we had to deal with. Next, please. So we said, all right, let's give Lavasa, India, let's let nature set the standard here. And we're setting what are called ecological performance standards. We look at the ecosystem services that the native ecosystem, which would be moist deciduous forest, we look at what services that provides, and those become the metrics, the lead standards, if you will, that we set for the entire city. Next, please. So for instance, just walk through these, please. We look as ecologists at what would the moist deciduous forest in India, how many gallons of water per storm would be intercepted first by the vegetation. 0 amount of rainwater hits the ground in those systems if they are properly vegetated, and then how much is stored. And that's what the development holds for itself as an aspirational goal, taking 20 years to achieve it, perhaps, but that's what we say. Solar gain and reflectance, we look at percentage of albedo. Carbon sequestration, we look at how much the native system would store in terms of carbon, and that's the level that we set for ourselves as the development. Next, please. Water filtration, percent of pollutants captured in the native system, that's our metric. Evapotranspiration, percentage of rainfall returned. This is an interesting one, because when the monsoons are falling, literally during the storm, water vapor is still evaporated up into the system. It literally volleys that moisture up into the air, creating clouds above the forest. And those clouds are then the generators of a monsoon farther inland. If you don't have that dynamic happening, you have droughts in inland India. So asking our development, buildings, hardscapes, softscapes, and plantings, to meet that same level of evapotranspiration is very important for an ecosystem service mimicking the native system. Nitrogen and phosphorus cycling. These systems create soil. And we in the city now have to think about doing that same thing. Next, please. Biodiversity, percent of diversity of native species. This is something we measure. Millimeters of soil created is something we measure and try to meet. Degrees of cooling. During those very hot times of year, forests actually cool the air around them. Can we ask the same thing of our buildings and of our cities? Next, please. So nature sets the standard in Lavasa, India. This is a picture of an artist's depiction of the Hilltown development. Next, please. When we went there, so now to the level of nature as model on technology, how we also look to the native organisms to see some technology cues. We take our cues from them. This is a nest of a harvester ant in Lavasa, in the Lavasa area that we actually saw. Interestingly, when you pour water on that nest, it goes down, it's as if it's a spiral staircase. It slows the water down so that there's not as much erosive force. And it also deposits, if there is silt being pulled, it deposits it in the corners. So the architects and the developers there are looking at a roadway system that would do the same thing, slow down this water, and where there is depositing silk on the corners. Next, please. One of the things we noticed was the use of roots, not just to stabilize soil, but in those areas in which there is heavy rainfall during one part of the year, and then it's very dry in another part of the year, you have what's called hydraulic redistribution. There are tap roots of certain species. And what happens is that, and then there are shallow roots in other species. During rainfall events, trees actually take in water from their shallow roots, move it down the tap root, and distribute it into the soil bank, therefore storing it for the dry season. And then roots reverse, and during the dry season, they pull the water from the bank where they've banked it, and then they distribute it to the shallow root system. Now this is something that, this two-way distribution of water, storing it underground so it doesn't have evaporative, so it's not subject to evaporation, is something that the developers, this broadened their conception of how they might store water. Next, please. Rooftop rain harvesting inspired by drip tips of forest trees. Something that those points on forest trees on leaves are very specific to purge the water away from the surfaces of the leaves as quickly as possible. It's part of this interception. The architects are thinking about ways to have awnings, things that catch water before it hits the ground and causes great erosion. Next, please. This is another area, but I thought I'd give you this example. Sediment collection inspired by the mangrove forest. Mangroves actually, as tides come in, those roots actually cause the soil to precipitate out, and similar engineering feats off of coastlines could stop plumes of soil from moving farther into the ocean. Next, please. Agriculture is going to be very, very important in Langfang. In this city, you still have a green belt of agricultural land, which is unique The North China Plain there, ecologically, that area is deep, deep alluvial soils from the mountains to the north and the west.